Okay, so the method of solution that we're going to be learning about in this video is going to be the method of characteristics, and we're going to look at it's going to be a very simple version. I mean, we're dealing with a very simple equation, but the method of characteristics is going to be the main method that we use when we talk about first order equations in this class. And just to make things a little more definite, we're not going to do lambdas and gammas for this problem. We're going to look at a specific problem, 2 times the partial derivative of u with respect to x plus 3 times the partial derivative of u with respect to y is equal to 0. And we're actually going to add a piece of information. We're going to assume that we know what u is along the x-axis. So we're going to assume that u of x0 is equal to f of x. And here, f is some given function. Okay, and so what we're doing, we're saying that we know what u is along the x-axis. In upcoming problems, what we're going to do is we're going to, maybe assume that we don't know f along the x-axis, but we know, or sorry, we don't know u along the x-axis, but we do know what u is along some perhaps more complicated curve, like a parabola or the y-axis or something like that. Okay, so we saw in the previous video that the curves that are parallel to 2, 3 are kind of important to this. So what we're going to do, the first step is I want to find all of the curves that are parallel to 2, 3. And so I'm going to write down a system of differential equations whose solution will give me the curves that are parallel to the vector 2, 3. Okay, so if the curve is parallel to the vector 2, 3, this means that the derivative x dot of t, the derivative of x with respect to, sorry, I'm not going to use t as my parameter, I'm going to use s. X dot of s is equal to 2, and y dot of s is equal to 3. Because if I have some curve, x of s, y of s, and it's parallel to the vector 2, 3, this means that the derivative x dot of s, y dot of s, this vector, is equal to 2, 3. That's what we mean when we say the curve is parallel to this vector, that its tangent vector is equal to, 2, 3. Okay, now this will make a little more sense when we do more problems, but I need to come up with initial values. So I want x of 0 to be some generic x naught, and I want y of 0 to be equal to 0. And the reason that we're doing that is because I want this initial condition, the x naught, the x of 0, y of 0, I want it to lie on this curve on which we know u. So we know u on the x-axis, so I want my initial point in these solutions here to lie on that curve. It just makes things more convenient. We don't have to do it that way, it just makes things more convenient. Okay, so now I have this system of equations. X prime is equal to 2, y prime is equal to 3, or x dot is equal to 2, y dot is equal to 3. Now I want to solve it. But this actually isn't such a difficult solution because it's not really even a legitimate system of equations, because we'd say it's decoupled. The x doesn't depend on y, the y doesn't depend on x, so I can just look at each one individually. So if I look at the x one, I've got, if x dot is equal to 2, this means x of s is equal to 2t plus x naught, 2s plus x naught, and y of s is just equal to 3s. So in other words, the curve that has parameterization 2s plus x naught, 3s, this is a curve that is parallel to the vector 2, 3 at every point, and it passes through the point x naught, 0. And so for every x naught, we're going to get a different curve. So this gives a family of curves, and again, for every x naught, for every point on the x-axis, we get a different curve. These curves are called characteristic curves. Of the PDE, and the method that we are learning, as I said before, and as the title said, this is the method of characteristics. Okay, and what we're going to see in the next page here is that along each one of these characteristics, I'm going to sketch some of them, and along each one of these characteristics, the PDE actually turns into an ODE, or reduces to an ODE. And I'll make that precise in just a moment. So let me just sketch like 3 sample curves here. So this one will start at the, x equals 0, 1. So it's parallel to the vector 2, 3. So the line, I'll go over 2 and up 3. We'll have something like this. And I'm going to set up almost all of the problems like this. So if you look through the notes, all the problems are going to have the same general setup, just because I think it's the best way to analyze the problem. As we look at more and more complicated problems, the analysis will get more and more complicated. But I think working in this framework, we'll see that even more in the next problem. Working in this framework, using this framework, I think just makes things easier. Okay, so I'm going to take this blue line kind of as a generic example. I'm going to call this point x naught 0. So the x coordinate is x naught, some generic point on the x-axis, and 0, again, it's going to be 0 all along the x-axis. And I'm going to define a u function z. Z of s is just going to be equal to u along this line here. So in other words, it's going to be u evaluated at the point x naught plus 2s, comma 3s. And as s increases, when s is equal to 0, we're here. As s increases, we're moving along the line this way. Okay, and so z of s, whatever, I don't know what z is, but I know that along this line here, u is equal to z of s. And now I'm going to come up with a differential equation that z satisfies. So I'm going to compute z dot of s. I'm going to compute the derivative of z with respect to s. So z dot of s. Okay, so now I'm kind of using the multidimensional chain rule here. If I look at u, so u is a function of the variables x and y, but each one of these, this is my x of s. This is my y of s. So when I compute the derivative of z with respect to s, I'm going to use the multidimensional chain rule, and I'm going to get dx, so dx ds, so x dot of s, times the partial derivative of u with respect to s, with respect to x, plus y dot of s times the partial derivative of u with respect to y. Again, this is just the multidimensional chain rule. Okay, but what is x dot of s? Well, x dot of s is just 2. So this is going to be 2 times the partial derivative of u with respect to x. Whoops. I don't know what happened there. This is going to be 2 times the partial derivative of u with respect to x plus 3 times the partial derivative of u with respect to y. But notice this is the PDE. If I go back to the last page, I've got 2 times the x derivative of u plus 3 times the y derivative of u is equal to 0. So in other words, this is just equal to 0. Okay, so I know that along this blue line, so again, z of s is u along this blue line, and I know that z dot of s is equal to 0 along the blue line. Okay, so my function, or z dot is just equal to 0. So z dot of 0 is equal to 0, and I know that z of 0, well, z of 0 is just going to be z evaluated at this point. So this is going to be z of 0 is equal to u. If I plug in x is equal to 0, I get, s is equal to 0, I get u of x naught 0. But I know what that is. That's just equal to f of x naught. I was given that in the problem. Okay, so now let me look at a generic point here on the line. So I'm going to call this, whoops. I'm going to call this point AB. And I want to compute what u is evaluated at AB. So u of AB. Okay, so now let's think about what's going on here. So u of AB, let me actually, okay, so now I can actually solve this equation. I've got z dot of s is equal to 0, z of 0 is equal to x naught. Well, if the derivative of z is equal to 0, this just means z of s is going to be equal to f of x naught. Okay, so z is constant, z dot is equal to 0, so it's constant, so it's just going to be whatever it's equal to at 0. So z of s is equal to f of x naught. Okay, now how can I use this to solve the differential equation? Well, if I think about just a generic point in the plane, AB, I know that u of AB, well, what I can do is I can kind of trace things back to this characteristic, or back to this point here, and I know that u of AB is going to be equal to f of x naught. But given an AB, I need to figure out what this x naught is. Okay, so given a generic AB in the plane, I need to figure out what x naught is. Well, how can I do that? Well, I'm going to solve these equations. I know that AB lies on a characteristic, and it goes to this point x naught 0. So I know that A is equal to x naught plus 2s, and I know that B then is going to be equal to 3s, because that's the parameterization for the line. X naught plus 2s is the x function, and 3s is the y function. Okay, so this tells me that, so now I want to solve this for x naught. Okay, so if I look at this equation, this tells me that s is equal to b over 3. If I take this expression for s and plug it in up here, this is going to be x naught, not s naught, x naught plus 2b over 3. Okay, so what this tells me, so x naught is equal to a minus 2/3 b. So then what this tells me, what this indicates is that u of AB is equal to f of x naught. Actually, let me just write it up there. Okay, so u of AB is equal to f of x naught. So this is equal to f of a minus 2/3 b. Okay, now the reason I'm using a and b instead of x and y is because I'm using x and y as the names of the functions for the parameterization. So now to actually answer the question, we're going to write things in terms of x and y. But AB is just a generic point in the plane. And I know that u of AB is equal to f of a minus 2/3 b. I can just replace the a and b with x and y now. U of xy is equal to f of x minus 2/3 y. Okay, and this is the solution to the differential equation. This is the solution to the partial differential equation. Okay, so I get that was a lot in this video. In the upcoming video, as you can see, we are going to have this very systematic way of working through the problems. And I think once we kind of do everything from top to bottom in one problem, or everything from top to bottom, one page, one problem, it'll make things make a little more sense. But that's it for this video.